Hi, welcome to the first video in our series on differentiation. We're really getting into kind of one of the meatier topics on the Year 1 Pure Maths course. And what I'm going to do is split this into kind of two parts, because there's going to be a lot of kind of talking and a lot of kind of theory behind it. But you need to know this stuff because you're going to have to do this in the exam. So let's say we'll split the videos into two bits just to make it kind of a bit easier to deal with. So here we go. That's what we've got to be able to do. So we're going to be looking at essentially gradients of curves, and we're going to be looking at kind of how we can use tangents and chords as estimators of those and understand the principles behind it. I'm not going to talk you through all of that. It will become clear as we go. And essentially what we're going to be doing, the key thing, is this last one down here. It's called differentiation from first principles. So that's what we're going to be doing in this video. So if we're ready, let's crack on. Up to now, you'll have seen gradients and work with gradients of straight lines. And by definition, let's say a straight line has got the same gradient throughout its length. And we should know change in y over change in x, rise over run, however you want to describe it. And the key thing is it's a straight line. So if I want to work out the gradients, change in y, change in x, gradient's 3/4. And it doesn't matter where I do that on the curve, the gradient is always going to be 3/4. Obviously enough. Now, this is referred to as dy dx, so we're going to be seeing this kind of notation quite a lot, and we're going to start using this as a way of describing gradients. And what we're doing is looking at that particularly in relation to curves. So, as we just seen, with a straight line, it's very straightforward, but how would you go about working out the gradient of that curve? Because you can see on this side of the curve, clearly we've got a positive gradient. On this side of the curve, the gradient is clearly negative. It's much flatter at the bottom, it's steeper at the top. Clearly the gradient is changing as we move around the curve. So how do we begin to start doing the process that we saw up here? And one way of doing this would potentially be to use the tangent. So we could draw a straight line as a tangent to the curve, go out a ruler, draw that line in, and so, well, you know what, the gradient of the curve at this point here is going to be the same as the gradient of the straight line, and we can do the whole kind of rise over run thing on the straight line. Problem with that one, though, is it does depend very much on how accurately we're able to draw the tangent, and generally speaking, the answer to that is not very accurately. So, yes, we could use the gradient and estimation. You might have seen that particularly at GCSE level, but it's not really the greatest technique in the world, so we need something a little bit better. One option, and this is the option we're now going to explore, is rather than using the tangent, is to look at the chord, and this is going to be the basis for differentiation from first principles. Now, you might be thinking to begin with, well, this is the chord here, and the tangent that we had before was much closer to the line, a much better estimation. You'd be right, but what we're going to do is look at this chord here and think about how we can get increasingly good estimates for the gradient. So, let's first of all just kind of have a look at that blue chord there. So, we've got 8/2, gradient of 4, but as we just said, yeah, the blue line is not particularly close to the curve, so it's not a great estimate. One thing we can do though is say, well, in order to get that chord closer to the red line, what we could do is just decrease the distance. So if I'm interested in this point here and the gradient at this point, rather than picking a point all the way down here, I can just imagine just saying, okay, rather than this point, let's just pick a point maybe here, and that would bring the chord a bit closer, or up here. And so the closer we get to our point that we're interested in, the better the chord is going to become as an estimator. So here we go. What we're going to do is have a look at this task here, where we've got 3 chords, and we're going to work out the gradients of each chord. In each case, we are moving the chord closer and closer to the red line. So if you want to have a go at doing this yourself, you might want to consider stopping the video as you calculate and fill in the table of values like that. Okay, so if you've had a little go yourself, hopefully you should find that you've got these values. So AP, that chord there, yeah, that distance there is 9, that distance there is 3, and so the gradient of the chord is 3. The BP, again, we're looking at the triangle here. So we've got 8/2, that was the one from the previous slide, and CP, there's the figures again. So we can see each time, each line, the blue line, then the purple line, then the green line, they're getting steeper, and you can see the green line, the green chord, is much, much closer to the curve than the other two. So it is the best estimator. But I've got to be honest, it's still not particularly good. So let's just continue this process and go a little bit further in. And so now I've really, really zoomed in. So here's our y = x² curve. Now I've overemphasized kind of the curve of it just so you can see what's going on. But what we've got, our point x is now at 2.9. Bearing in mind we want to find the gradient when x is 3, so I'm like 1/10 of a unit away from this point down here. And then at this point here I'm 1/100th away, and here 1,000th. So we've really zoomed in. So let's have a look at what that does with exactly the same thing. And again, you might want to have a go at doing this yourself. So if you feel like you want to pause the video, please feel free and have a go at coming up with the values yourself. And if you've done that, what we'll find is we get those values there. And so what that gives us is the gradient xp has got a gradient of 5.9, yp 5.99, zp 5.999. And hopefully you can see that if we got even closer, let's say at z, we're 1,000th of a unit away, maybe go to 10,000, 100,000 minutes, what we're going to get is just more 5.99999s and so on. So eventually what is happening here is that as we get closer and closer to 3, the gradient is getting closer and closer to 6. So mathematically speaking, what's going on here, we can say that as x tends to 3, and that arrow there means tends to get closer to 3, then the gradient, and it's this thing here, the gradient tends to 6. Now you'll notice here I've used slightly different symbols. We've got these kind of lowercase Greek deltas, which just means change in y over change in x. So saying that the gradient is becoming, the gradient is becoming 6. Right, so that's the statement of what we saw previously. And let's say a little bit of notation with it. Those are the delta things that I mentioned on the previous slide. And we said that that was the notation we used to describe gradient. And mathematically what we write is as the change in x, the distance from our point in our chord to our actual point we're interested in, as that distance becomes smaller and smaller, i.e. tends to 0, then the change in y over change in x tends towards this thing dy dx, which we can use as being the actual value of the curve. Right, so again, another task. We've got our y equals x squared curve, and we saw that when x was 3, the gradient was 6. So again, what you might want to do now is have a go at trying exactly the same technique from what we saw in the previous slide at different points for x. So if you want to have a go at that, again, pause the video. And if you'd rather just see what happens, we'll chuck some values up for you now. So when x is 0, the gradient is 0. When x is 1, you should have found the gradient was 2. When x is 2, the gradient is 4. 3 is 6 we've already got. There's 4. And there's the gradient was 10 when x was 5. And hopefully we can see very clearly here that as the gradient changes as the x coordinate changes. And clearly there's a mathematical rule, a very obvious one. So what we're saying is the gradient is a function of x. The gradient of the curve depends on the value of x, i.e. where you are in the curve. And in this particular case, we say that for this curve, y equals x squared, then dy dx equals 2x, because clearly we can see that the gradient each time is double the x coordinate. So what we've got now is our gradient function dy dx equals 2x, and so we know that any point on the x squared curve, all we've got to do is take the value of the coordinate where we are, double it, and we've got the gradient. Okay, so moving on from that, what we had on the previous slide was a very numerical way of doing things. Let's just have a look at how we can do the same thing algebraically and just see what results we get. Again, we're going to look at y equals x squared. So again, here's my curve. What I've got this time is the blue chord here. That's going to be my estimator for the red curve. And this on y equals x squared. So if I've got the x coordinate is x, at this point here, the y coordinate is going to be x squared. But up here at the top here, I'm going to say, well, I'm just going to move a little bit further along the line. So I've got the x coordinate is x plus h just being that little bit extras. And so therefore the y coordinate is the x coordinate squared, so it's x plus h squared. So what we're saying is this distance h, that's essentially this bit here, is just a very small distance. And so let's have a look at what's going to happen with our estimator for this straight line now. So here we go. The change in y, so what we're going to need to know is that distance there, and so that's the difference between the y coordinates. We've got x plus h squared minus x squared, so that's that bit, and the change in x, which is going to be that bit there, is going to be the difference between the x coordinates, so it's going to be x plus h minus x. So we've got those two things, and obviously we need to do change in y over change in x. So the gradient, or delta y, change in y over change in x, is given by that thing there. So the change in y, change in x. Multiplying out the brackets, we get x squared plus 2x plus h squared minus x squared, and on the bottom x plus h minus x again. And obviously we can do a little bit of simplifying and cancelling out here. That x squared is going to disappear against that one. On the bottom the x's are going to disappear, and so what we're left with is that expression there. So that being done, we can now take that a little bit further. On the top, clearly we can factorise and take an h out of the brackets, and now those h's are going to cancel, and so what we end up with is the whole thing becomes this expression down here, which is 2x plus h, and already you can see that 2x from the previous slide starting to appear. But what's happening with the h? Well, what's happening is we've got our change in y over change in x is that, and then we say, well, as h becomes smaller and smaller, h tends to 0. So essentially what we're going to do is kind of move this point up the curve like this. We're going to make the difference between our x coordinate here and our x coordinate here smaller and smaller and smaller until essentially that point there, a, effectively becomes on top of b. So we're going to make h tend to 0, so they become infinitely close together. And if h tends to 0, then dy dx, well, that bit there, that h is going to become 0. So dy dx tends to 2x. So what we're saying is dy by dx is 2x, and there's the result that we had from our numerical approach. And in the exam, you're going to have to demonstrate the technique that we've just gone through on this slide. But that's how I'll formalise that and look at all that for you in the next video. Before we get to that, I just want to kind of get into the crux of differentiation and how it's all going to work. So let's just have a look. Now we've been looking at y equals x squared, but again what we need to do is now have a little look at different polynomials. So we've got straight line, which we know about there, but our cubic there, power 4 there, just to see how all that works. So again, if you want to have a go at doing these for yourself, that's how I say, okay, go back and have a look at the previous slide in the video, and then just apply exactly the same techniques to the 4 functions there and see how you go. If you've done all that, what we should have found is there's our y equals x squared, gradient is 2x. If we go back to y equals kx, part A, we should have found the gradient was k, which we already knew because it's a straight line. For y equals x cubed, we should have found that the expression for the function of the gradient is 3x squared. And for x to the power 4, we should have found that it becomes 4x cubed. And hopefully now you're starting to see a pattern starting to emerge. So if we just take, for example, those two, so x to the power 10, what's going to happen? Well, you can see, if I have a look at x to the power 4, the 4 is now appearing here, and the power is 1 less. The 3 is appearing here, and the power is 1 less. So for this one, we can say, well, that's going to become 10x to the power 9. And for x to the power n, so this is our general polynomial, for n being any number whatsoever up there, we're going to get nx to the n minus 1. And here comes the punchline. The final bit that we need to know is if you've got y equals x to the power n, a polynomial that you're differentiating, to find the gradient, you just need to do nx n to the minus 1, which is the result here. And you might, or we will actually see it written slightly differently as a function. So using function notation, this is exactly the same thing. If we've got a function of x, which is that, then the gradient function, f dash x, is that thing there. Now, if the mathematical notation looks a little bit scary, it's much easier to break it down into a simple kind of two-stage process. And the way to think of it is to say, well, you know, what we've got to do is, firstly, bring the power to the front, and secondly, knock one off the power. And I think what I'm going to do is stop this video here, because I think that's more than enough information for one video. And in the next video, we'll go back and we'll look at kind of a formal process for differentiation from first principles and what you're going to be able to do in the exam.